Thanks. Okay, so we're entering the last week of the course. I have some great material to finish with. Property T and sort of an overview of how everything we've talked about fits together. I wanted to start with a couple of administrative remarks. So first, there will be a Q guide entry for this course, i.e. a survey of students who took the course, giving feedback on it. I really value that feedback. So please do fill out the Q guide. Also feel free to email me now or later after the course is over with any suggestions or guidance on how to make it better in the future, what worked well, what could be improved. That would be super helpful. This week, my office hours will be at 4 p.m. on Wednesday instead of 2, still the regular Zoom URL. So please feel welcome to attend. I should say that I've already posted the last homework. So the last homework, for those who are doing the homework, will be due next Tuesday, as usual, but it's posted now. If you want to get an early start on it, and as usual, you'll just email your answers to Carl, who will, continue to hold section and office hours this Friday and Monday, and then the formal part of the course will be over. Okay, so I want to start by telling a little story about the incompatibility between the Euclidean or even spherical world that we live in, if we think of ourselves as living on the surface of the Earth, and trees, and more generally non-amenable graphs. So one story is that when Bill Thurston was taking his qualifying exam as a graduate student at Berkeley, he was asked to give an example of a universal covering space. And instead of doing what every other student does, describing how the real line covers the circle, he described the universal covering space for a surface of genus 2. And he started by saying, well, a surface of genus 2 is just obtained by gluing together the sides of an octagon. So we have to make sure we have 8 sides, not 6. And then, you have to put another octagon up here and another octagon up here. And actually, there's many coming together. You're identifying opposite sides. So you have to get another one in here, and then another one in here, and then another one here. And since the blackboard is not hyperbolic space, you very quickly just get a complete mess. And so, in fact, he got a conditional in topology on his qualifying exam. And this just illustrates the tension between the exponential expansion we see in a tree and the polynomial growth we see in the world where we live. So I often start drawing a tree, but I never get very far because you have to put so many vertices in such a small area. So there's this fundamental tension between trees and the physical world. And yet a tree is a natural model for ancestry. One organism gives birth to 3 more, which give birth to each to 3 more, and so on. And there's a beautiful passage in Darwin's Origin of Species that I think captures this very nicely. I just like to share it with you. It says, if during the long course of ages and under varying conditions of life, organic beings vary at all in the several parts of their organization, and I think this cannot be disputed, if there be, owing to the high geometrical powers of increase of each species at some age, season, or year, a severe struggle for life, and this certainly cannot be disputed, then considering the infinite complexity of the relations of all organic beings to each other and to their conditions of existence, causing an infinite diversity in structure, constitutions, and habits to be advantageous to them, I think it would be a most extraordinary fact if no variation ever had occurred, useful to each being's own welfare, in the same way as so many variations have occurred useful to man. So first, I love this because it's the longest scientific sentence that I'm aware of. That's a single sentence. And secondly, he captures how this competition between exponential growth and polynomial resources is sort of the fundamental, the crux of the mechanism, the engine of natural selection. But in retrospect, I think we can say even more than what Darwin is observing about this tension between these non-amenable graphs and our amenable world. What actually happens is that the graphs of relationships between organic beings, they're not infinite trees, but they are expanders. They're graphs, they're small worlds where individuals don't have a lot of direct relationships to many other individuals, but the chains of relationships between individuals are really rather short. And so I think the sequel to Darwin's thought is that the ecosystems that we see are really like expanding graphs, not like trees, although they might look like trees at a fairly large scale. And sort of what happens is there's this flourishing, this tree-like growth to a certain extent, and then it becomes truncated by the limitations of resources. And we have all these small trees coexisting in this expanding graph. Okay, so let's, with that in mind, let me return to the discussion of expanders and use that to motivate the last couple of topics I want to talk about, which are the Laplacian and property T. So any questions before we go on? Insightful comments about my somewhat comical brief discussion of evolution? Somebody who knows more biology. Okay, so I want to turn now to the Laplacian. And I'm going to start out by talking about the Laplacian on a compact Riemannian manifold. So we have a manifold with a metric. And the way you should think of the Laplacian is it's actually just a convenient way of describing a certain quadratic form on the space of smooth functions. So if you have a smooth function on your manifold with compact support, of course, there's a natural norm on the space of such functions, which is the L2 norm. So this is just the integral of the absolute value of f squared with respect to the volume attached to the metric g. And I'll suppress the volume in future integrals. But there's another quadratic form, which is you could define a different norm of f, and it will also be an L2 norm, but let me put gradient underneath here, and it will just be the integral of the absolute value of the gradient of f squared. Both integrals being over our compact manifold. Actually, since our manifold's compact, I can just say C infinity functions. Okay, now, when you have two inner products on the same space, you can express one inner product in terms of the other using a self-adjoint operator. And that's what the Laplacian is for. It's a self-adjoint operator that allows one to express this second norm in terms of the original L2 norm here. And you'll notice that this is greater than or equal to 0. So for this definition, the Laplacian on Rn is given by minus the sum of the second derivative squared. When you integrate by parts, you get a positive operator. Okay, now, how else can you think of two inner products on the same space Well, think of what happens if you have a positive definite inner product on Euclidean space. Then the locus where you have, say, QFF, this is our new inner product, you can look at the locus where this is equal to 1. And this will be some sort of an ellipsoid in Rn. And to analyze this ellipsoid, you might first look for the shortest axis of the ellipsoid. And then you might look for the shortest axis that's perpendicular to this axis, and so on. And indeed, this quadratic form can be diagonalized, as can any symmetric matrix. And the diagonalization process can be carried out inductively. You first look for the shortest vector with respect to this inner product, and say of norm 1 with respect to our original Euclidean inner product, then the shortest vector of norm 2, and so on. So similarly, on a compact manifold, the Laplacian can be diagonalized. We can write the Laplacian as equal to lambda naught, lambda 1, lambda 2, etc., for some increasing sequence of real numbers, all positive, with respect to a basis, Fi, and in fact an orthonormal basis for not just the smooth functions on M, but on all of L2 of M. And associated to each of these eigenvalues, there's an eigenfunction, whose Laplacian satisfies this condition, and the integral of the absolute value of Fi squared is equal to 1. So how do you find these eigenfunctions of the Laplacian? Well, the first thing you do is, as I said, you look for the function whose size, and let me give a shorthand for this. This is sort of the energy of the function. If we think of it costing the function energy to have a non-trivial gradient, we look for the function of smallest energy. Now we're on a compact manifold, so the function with smallest energy is the constant function, whose gradient is 0. So to diagonalize the Laplacian, first we look to minimize the energy of F, subject to the condition that the norm of F in L2 is equal to 1. And what we find is that F is equal to a constant. In fact, F is equal to 1 if the volume of our manifold is equal to 1 suffices. This has energy equal to 0. So the first eigenvalue is equal to 0. And this is the first element in our orthonormal basis. Now what we do is we take the orthogonal complement of this element and we try to minimize the energy again. And this is where it starts to get interesting. So the next thing we do is we minimize E of F subject to the conditions that the norm of F in L2 is 1 and that F is perpendicular to F naught. And what this means is very simple. It means that F is in L2 0 of M. In other words, the integral of F is equal to 0. So on a connected manifold, that can be hard to do. You have to have your function be positive somewhere and it has to be negative somewhere else so that the integral will end up being 0. And it has to have definite mass since the L2 norm is 1. So there must be some place in the middle where the gradient of F is non-zero. And so in fact, lambda 1 is always positive, and the size of lambda 1 is somehow measuring how hard it is to disconnect the manifold. Because to minimize lambda 1, you want to cut the manifold into two pieces. The place where F is positive and the place where it's negative, and then minimize this region where there's a transition. So if you had a Riemann surface with a short geodesic, then you could make your function equal to 1 here, equal to -1 here, And then the gradient could be concentrated in this collar around the short geodesic with small volume. That's where the gradient of f is about 1. And what you would find is that lambda 1 is very close to 0 in the case where the surface can be easily separated. Okay, now I'm not going to use the rest of the spectrum in this talk. The most interesting thing for us are lambda 0 and lambda 1. But I want you to notice the obvious comparison between lambda 1 and the notion of an expanding graph. An expanding graph is one that you can't cut into 2 pieces very easily. If you try to cut it into 2 pieces, the size of the boundary between the 2 pieces has to be comparable to the size of the smaller piece. And so having lower bounds on lambda 1 is very closely related to expansion. But I should say that in general, to calculate lambda I, you just minimize E of f subject to the norm of f being equal to 1 and f perpendicular to the eigenfunctions that you found so far. Okay, so there's a fairly routine way to do this and then also to prove that at the end of the day you get a basis for L2, and elliptic regularity assures that all of these eigenfunctions are actually smooth. Okay, now the next question I want to think about is what happens to lambda 1 when we take a covering of a manifold? So what can we say about the relationship between lambda 1 on 2 manifolds, which are very simply cousins, in the sense that one is, say, a finite cover of the other. So M continues to be compact, and then we take a finite cover, maybe even a Galois cover, Mg, so G is finite. And now we ask, what can we say about lambda 1? I'm assuming everything remains connected. Well, if we had an eigenfunction of the Laplacian down here, we could certainly lift it to an eigenfunction up here. And if it was perpendicular to the constants down here, it would still be perpendicular to the constants up here. So all of the functions in the minimization competition downstairs give entries in the minimization competition upstairs. And so lambda 1 of M tilde is certainly less than or equal to lambda 1 of M. So if you have a tower of coverings, then the least eigenvalue of the Laplacian after the constants always goes down. It can't possibly increase. And in fact, it can go down very rapidly. So for example, example 1, if you have a surface of genus 2 that looks like this, this is M, and we have a very short geodesic here, you might think, oh, lambda 1 can be very small, but actually it can't, because you might try to make a function that's +1 here and -1 here, does this rapid transition here, but they also have to do a rapid transition some over here in the thick part of the manifold. So in fact, as the length of this geodesic goes to 0, lambda 1 of M does not tend to 0. So lambda 1 here remains comparable to 1 no matter how thin this geodesic gets. But if you take a 2-sheeted cover, by cutting open this geodesic, taking 2 copies and gluing them together, you get a manifold that looks like this. And now this short geodesic separates the manifold. There's 2 copies of it, but if this was short, 2 times short is still short. And now we can make our function that's +1 here, -1 here, and has small gradient. So here, lambda 1 is approximately equal to 0. It tends to 0 as the length of this short geodesic goes to 0. So if you want to have big lambda 1, it's dangerous to take coverings. So example 2, which was a homework problem, if we let M be the usual torus Rn mod Zn, And inside of Zn, we take a sequence of sublattices where the index of this lattice Zn colon lambda I goes to infinity. You then get a sequence of covering spaces, Mi, or n mod lambda I. And it turns out no matter how you choose these sublattices, lambda 1 of Mi goes to 0. So if you start with a torus of any dimension and start taking coverings, in fact, you're forced to send lambda 1 to 0. And the reason for this is that there's a simple formula for lambda 1. In fact, lambda 1 is equal to the length, absolute value mu, of the shortest vector in the dual lattice in lambda I hat, which is ham lambda I into z. It's the vectors that have an integral inner product with every element of lambda I. And these lattices, these lambda I hats, start out being equal to Zn, and then they get bigger and bigger and bigger. And so if you take the Zn lattice and you start enlarging it to make bigger and bigger lattices, the length of the shortest vectors in those lattices has to go to 0. So it's hard to make infinite towers of coverings where lambda 1 stays bounded below. But it turns out there's a beautiful family of examples that we've glimpsed several times where lambda 1 does stay bounded below. And these are a good source of expanding graphs, but the fact that lambda 1 stays bounded below is of interest in its own right. So let me describe these examples. So first, we have the group PSL2Z, which acts on the upper half plane. And we can map this to the finite group PSL2 of Z mod n. For each n, this turns out to be a surjective map. And the kernel is called gamma of n. And it's just equal to the matrices such that A is equal to the identity mod n. So that's a finite index subgroup of the group of integral matrices. Now, of course, we have the covering space, the quotient space, what I'll call gamma 1. After all, gamma 1 would just be the map to the trivial group. So this group here is sometimes called gamma 1. So it fits into this chain groups gamma. Gamma 1 mod H is our friend, the 2, 3 infinity orbifold. But for each one of these subgroups, we get a covering space of H mod gamma 1 of the modular surface called Xn, which is gamma n mod H. Now, let me remind you where you have seen some of these X of n's. So at some point, we discussed spherical geometry, and we fairly quickly dismissed it. But before we did, we found all the finite groups that act on the 2 sphere. So you'll recall that if you take the 2 sphere and you mod out by the action of a discrete group of isometries, which is certainly has to be finite, there are a couple of possibilities for what you get. So one set of possibilities you can get are the 2, 3, n orbifolds, where n is equal to 2, 3, 4, and 5. And then it stops because those orbifolds start to have negative Euler characteristic. So there's quotients of the sphere that look like this, 2, 3, n. And this group gamma presents those as being covered by the sphere. Well, interestingly enough, those groups account for x2, x3, x4, and x5. So this is x1 here. And what does let's go all the way up and look at an interesting example. What does x5 look like? So that's gamma 5 mod h. And in fact, it's closely related to the dodecahedron. So there is this tiling of the sphere by pentagons. Sorry, this is not very convincing. All of these figures are, the faces are 5-sided. So you can take the tiling of the sphere by pentagons, and then you can think of this as the Riemann sphere. And then you can think of this deck group here, gamma, as being the group, it turns out that A5 is the same thing as PSL2 of Z mod 5. And then the quotient space is the 2, 3, 5 orbifold. But now there's an inclusion of the 2, 3 infinity orbifold into this one, where you just puncture this orbifold at 5, and this spherical orbifold suddenly becomes a hyperbolic orbifold. And what's the corresponding covering space here? It just means we have to puncture the 2 sphere at the preimages of this 5 point. And those are just the face centers of the dodecahedron, of the pentatagonal faces of the dodecahedron. So x5, which is the quotient of PSL2 of the upper half plane by this congruent subgroup, gamma 5, is nothing more than C hat minus 12 points with A5 symmetry. And for exactly the same type of reason, x4 is the sphere, or if you like, it's a cube as a Riemann surface with its 6 face centers punctured. So it becomes a hyperbolic surface. And then that covers the modular orbifold with a deck group PSL2 Z mod 4. And this turns out to be isomorphic to S4, just like this one was isomorphic to X5. And then X3 turns out to be the tetrahedron with its faces punctured. So 4 punctures there. The group is PSL2 of Z mod 3. And then X2 is the triply punctured sphere. And the deck group is PSL2 of Z mod 2, which is isomorphic to S3. Okay, so these congruent subgroups provide a beautiful sequence of covering spaces of the modular surface. And since the modular surface has non-abelian fundamental group, there's a better chance that lambda 1 might remain bounded below. Now, you might be troubled by the fact that there's only 5 Euclidean solids, but this sequence just keeps going up. In fact, let me skip ahead a bit. It turns out that X6 is not a sphere anymore. It's a multiply punctured surface of genus 1, and X7 has genus 3. In fact, X7 we've looked at before. This is a famous surface of genus 3 that can be tiled by heptagons, 24 7-sided polygons. And it covers the 2, 3, 7 orbifold, which is hyperbolic. And when you puncture this surface at the centers of all of these heptagons, you then get the modular surface X7. And its deck group is this beautiful simple group of order 168, which is nicely presented as PSL2 of Z mod 7. And so on. So indeed, these congruence covers of the modular surface give an infinite tower of Riemann surfaces, and their genera go to infinity. And they include many interesting and familiar, very symmetric Riemann surfaces. Okay, so now I can announce a famous conjecture. This is sometimes called the Ramanujan Conjecture, for reasons that are a bit complicated to explain. The conjecture is that λ1 of xn is greater than or equal to 1/4 for all n. So unlike the case of the torus, these surfaces all remain very well connected together. They're hard to break into two pieces. Of course, this is just a conjecture. However, there's a theorem due to Selberg that says this conjecture is true with 1/4 replaced by 3/16. And this constant has been variously improved, but still no one's gotten to 1/4. Okay, so let me say a couple of things about this conjecture. First, 1/4 turns out to be the same as lambda naught of the hyperbolic plane. So in some sense, this conjecture is saying that these modular surfaces are like mini hyperbolic planes, in the same way that expanding graphs are like mini trees, in some very precise sense. This second thing I want to say is these manifolds, they're complete hyperbolic manifolds, they're finite volume, but they're not compact. And in fact, the Laplacian cannot be diagonalized on these manifolds. There is not a basis of L2 eigenfunctions, but it doesn't matter. So in general, what do we mean by λ1 here? We mean the value you would guess by looking at the minimization problem. So this is the if over the integral of f is equal to 0, the integral of f squared is equal to 1, of the integral of the absolute value of the gradient of f squared, d volume. So we just take that to be the definition of λ1 of such a finite volume manifold. Okay, so this is a beautiful conjecture. It has interpretations in terms of representation theory. The proof uses some sophisticated number theory, Kloosterman sums. But in any case, I want to take this for the moment as a black box and derive from this a corollary for you. So as a corollary, I'm going to construct a sequence of graphs. And the graph is going to be equal to the Cayley graph of PSL2 Z mod n with respect to a certain generating set. Now, what generating set am I going to use? Well, this is the image of PSL2Z. So once I pick a generating set for PSL2Z, I get one for PSL2Z mod n. So I just need to pick generators for the fundamental group of this orbifold. And one nice pair to pick is a loop that goes around here and a loop that goes around here. Because the product of those two will give a loop that goes around the 3, and that generates the whole fundamental group. So for my generators, I'm going to take very concretely the matrices 0, 1, minus 1, 0. That's an element of order 2 in PSL2. And a loop around the cusp, which is this parabolic element 1, 1, 0, 1. Okay, this is my generating set S. And of course, the Cayley graph is then I take points of PSL2Z mod n, and then I connect them when they differ by these generators. So I get a sequence of graphs that is, it's actually trivalent, because this has order 2, whereas this does not. In any case, their degrees are bounded, and the corollary is that this is a sequence of expander graphs. so this is one of the concrete ways one can produce graphs with these good expansion properties by leveraging results from geometry and automorphic forms. Let me just say a word about the proof. I sketched the proof last time, and the proof should be almost obvious. So the proof should be something like this. You tile xn by, let me call this group here Gn, by cardinality of Gn polyhedra, polygons, permuted by Gn. So in other words, we choose a fundamental domain for PSL2Z, and then it gives tilings of each of these covering spaces of H mod PSL2Z. And so we have our surface Xn, and we cut it up in these pieces. We have a fundamental domain here, and then G times that, and so on, H times that. And so then we have a bijection between the tiles and the points of Gn. And it's essentially true that two tiles are adjacent if they're connected by an edge in the graph. Now, it's not quite true, but what is true is that they're within one or two edges of one another. So if I enriched the generating set a bit here, which wouldn't change the expansion property, it would literally be true that tiles are adjacent if and only if they're connected in the graph. And so now I say, if this graph Gn is not an expander, then I can write the group Gn as the union of two sets A and B, where the size of the boundary of A over the minimum of the size of A and the size of B is as small as I like. And then I just take the tiles corresponding to A times B, and the rest of the tiles corresponding to B times D. And I build a function of mean 0 that's constant here, and then it makes some transition along the boundary. And then since the boundary is small relative to the size of the two tiles, this integral of the gradient of f squared is much smaller than the integral of f squared, and we contradict the fact that lambda 1 is uniformly bounded below. So I just wanted to make you aware that there is a technical nuance in this argument, which is sometimes left over, which is that the tiles are, in our case, are not compact. And the reason is that these Riemann surfaces are not compact. The fundamental domain for SL2Z is not compact. So actually these tiles go off and get very narrow. And then when you have two tiles that meet along a very narrow strip, you really don't want to make a function that's 1 here and 0 here, because then the gradient will be super intense along this very short, this very narrow region where it has to make the transition from 0 to 1. So there's a technical argument where you cut off the tiles and use that to modify the construction slightly. I'll just mention the fact that that technical argument exists and that the proof goes through anyway, even though just as if the quotients were compact once you've made that modification. Okay, so this is kind of an introduction to congruence covers, eigenvalues of the Laplacian, and their use in constructing expanding graphs. So any questions on this circle of ideas? Okay, so now I'm going to set this aside and go on to a final topic, which could really be the beginning of a course in its own right, which is property T. And I should mention that property T fits in to a very large circle of ideas called superrigidity for Lie groups of higher rank that was established by Margulis. So we're just going to kind of touch the tip of the iceberg and get a glimpse of what's special about these Lie groups. So what we're going to see is a pretty unusual phenomenon that we haven't seen before in our ergodic theory discussions. We're going to see a way in which SL3R is different from SL2R. Okay, so property T. I should probably write this out in full one. So David Kazdan, former teacher and colleague of mine here at Harvard, invented this, gave it the unimaginative name of property T. Stuck. So what is Kazdan's property T? Well, let me remind you of some notions. So suppose we have G, which is, let's say this is a locally compact group. So it might be a discrete group, it might be a Lie group, and then we have a unitary representation on U of H. Now there's two competing properties here. One is the notion of invariant vectors. Of course, an invariant vector is one just such that G dot F equals F for all G and G. It's fixed by everything in G. The space of invariant vectors is often denoted by H super G. And of course, when we're looking for these, we're interested in the non-zero ones. So invariant vectors, in the case of ergodic theory, correspond to the failure of ergodicity. So in ergodic theory, we would let H be L2 0 of some measure space on which G was acting. And in the ergodic case, there would be no invariant functions of mean zero. Any invariant function would have to be constant. And so the absence of invariant vectors is what we think of as ergodicity. So maybe I should say the important notion here is not so much invariant vectors, but no invariant vectors. The situation where H of G is equal to 0, and this might be called ergodicity. And then there's the notion of almost invariant vectors. And this notion is almost what you might guess, except it's not, doesn't mean there's a vector that's moved only a little bit by G. What it means is that for each compact subset of G, there's a vector that's moved by only a little bit by that compact subset. So the way to talk about this is the following. Let's let K contained in G be compact. And then we define the variation over K of a vector F to be the sup over G and K of the distance that G moves F divided by the norm of F. And then we say that G has almost invariant vectors if for all compact set K contained in G, there exists Fn and H, of course non-zero, such that the variation over K of Fn goes to 0. Now, by the way, when we look at discrete groups, we often require they're finitely generated. When we look at Lie groups, we can almost always choose a compact set which generates the whole Lie group. And so, in fact, if G is generated by K as an algebraic group, which frequently happens, for example, if G is a connected Lie group, any compact set that contains an open set around the origin will generate the group. If G is generated by K, then suffices to test just this K. So rather than saying for all K, we can just say pick a generating K. Almost invariant vectors means there are vectors which are barely moved by this compact set K. Okay, so let me remind you about this notion because we've used it once already. So there are three definitions of amenability. So if G is a discrete group, then amenability is equivalent to 1. There exists a G invariant mean, a map from L infinity of G to R, satisfying the appropriate conditions. Secondly, there exists a sequence of Fulner sets in the Cayley graph of G, so the boundary of AN over the size of AN goes to 0. And third, the action of G on the L2 functions on G of mean 0 has almost invariant vectors. And for the amenable groups that we know well, for example, the integers or the real line, these invariant vectors are essentially obvious. So for example, on the integers, that's an example of an amenable group. We just take the interval from -n to n. We take the function that's 1 there and is 0 everywhere else. We take our compact set to be the element 1 because that generates Z. And then when we take this function and we move it over by 1, it barely moves in the L2 norm. And so indeed, the regular representation of G on the mean 0 L2 functions has almost invariant vectors. Sorry, this should have been just on L2 of G. Okay, so Constant's property T is very similar to the contrapositive of amenability. In other words, it's like a strong form of non-amenability. So non-amenability says this representation does not have any almost invariant vectors. And Constant's property says that there are no interesting representations with almost invariant vectors at all. So the definition is G has property T if whenever this representation rho has almost invariant vectors, it has invariant vectors. And so, for example, this group obviously doesn't have property T because we have these almost invariant vectors, but we can't have an invariant vector in L2 of Z because it would have to be constant everywhere and then it wouldn't be in L2. Okay, let me turn this definition into something that's more quantitative sounding. And it's not quite obvious that this definition is equivalent, but it is. And I'm going to give the definition in the case where G is in fact generated by a given compact set K. So what it says is there exists a lambda which depends on K and is greater than 0 such that whenever rho is ergodic, meaning no invariant vectors, let me just write that economically as Hg equals 0. The variation over K of F is greater than lambda, greater than 0 for all F in H. Now, let me just say a word about how representations theorists view this. Representations theorist imagines that even when a group is non-abelian, there's some sort of thing called G hat, which is the space of unitary representations of G, some sort of dual space. And in this dual space, there's the identity representation or the trivial representation. And now, what does a representation with almost invariant vectors give you? It gives you some representations that accumulate on the identity. And the definition says the only way you can get representations that accumulate on the identity is to have the identity in there from the beginning. It has invariant vectors. So the way representations theorists think of this is the rest of G hat is over here. There's the trivial representation, and then there's the honest, interesting unitary representations of G, and never the twain shall meet. These do not ever get close to these. And that's what this definite movement of every vector in H amounts to. Okay, so before we start proving things about property T, I'd like to do a little exercise like we did in the case of amenability. Namely, we should try to list some examples of groups with property T and some examples of groups that don't have property T. Okay, so I'm gonna, and also some little lemmas that obviously hold, i.e. if this group has property T, then this other group has property T. So let's make two columns, not T and T. Okay, so there's actually a very easy class of groups that does have property T, for which the existence of an almost invariant vector implies the existence of an invariant vector. Can anybody give me an example of just one non-trivial group with property T? Think small. So I'll give you an example, and then somebody try to explain to me why this group has property T. So the first example of a group with property T is Z mod 2. So if you have Z mod 2 acting on a vector space, and it has a vector of unit length that's barely moved, then in fact it has a fixed vector. In fact, you should easily be able to construct that fixed vector from the vector that's barely moved. How would you do that?
Could you take like some average of that vector that barely moves and the one based on the action from the non-zero element in Z2?
Yeah, absolutely. So here's our vector F. Here's GF. And this is the whole orbit of F under the group because F is the same as G squared F. So this pair of vectors is invariant under the action of the group. So if I take, for example, their sum, F plus GF, when you apply G to this, it just permutes the elements in the sum. And so of course it's fixed. Well, the same argument applies to Z mod 3. Also, it applies to S3 because I made no use of the fact that the group was abelian. So what do you think is a general class of groups here that have property T?
Finite groups.
Okay, good, finite groups. Now there's a generalization of finite groups to topological groups. What kind of Lie groups behave like finite groups?
Compact ones.
Compact, excellent. So in fact, finite groups and more generally, compact groups have property T. For exactly the same reason. If you have a compact group, then you can take K to be the whole group. And then you get a vector which barely moves at all under the group. And then you replace it by its average over the group, and it's a non-zero vector, and it's obviously fixed because you averaged. Okay, so interestingly, property T sounds a little bit like some souped up form of non-amenability. But actually, these groups are amenable. Of course, you can average over finite groups. But that's sort of it. So as we start looking for more interesting examples of property T, beyond this, it turns out the groups have to be very big. And in particular, they have to be non-amenable. So in fact, let's look at some groups that are not property T. So one example is the integers. As we just saw, the integers acting on L2 of the integers has almost invariant vectors, but no invariant vectors. And in fact, if G is a discrete group and it's infinite, and G is amenable, then this implies that it's not T. And the way you prove this is you just consider the representation of G acting on L2 of G. This does not have any invariant vectors, but amenability means it has almost invariant vectors. So it contradicts our hypothesis here. So that means once we exclude these compact groups, T implies non-amenability. So let's just record that over here. If G is non-compact and it has property T, then it certainly is going to be a non-amenable group. Okay, now here's one of the reasons why the use of all unitary representations is so powerful. Suppose I have a quotient group of G. I map G onto some group G prime. And now I want to analyze some representation rho prime of G prime. Well, any representation of G prime gives me a representation of G just by factoring through. So in fact, once G has property T, so does G prime. Because if this representation has almost invariant vectors, then so does this one. But then this one has fixed vectors, and so this one also has fixed vectors. So it's just trivial from the definition that T passes the quotient groups. So if G has T, this implies G mod n has T for any normal subgroup n. So it passes to quotients. So here is where we start to see the divergence between amenability and property T. I'm putting Z star Z in this column. Our friend, the free group, the biggest, most expansive group we know, actually is not that big. It doesn't have property T. Why doesn't this group have property T? Using the little lemma I just wrote down.
It has finite quotients?
Yeah, is it louder?
It has finite quotients?
Well, that's okay, right? So if the quotient has property T, big deal.
Oh, right, yeah.
These groups do have property T. But if it had a quotient that didn't have property T, then it itself couldn't have property T.
And Z is a quotient.
And Z is a quotient, thank you. So since the free group maps onto Z, and this does not have property T, this doesn't either. And indeed, we can take the representations of Z that prove it doesn't have property T and use those to prove this doesn't either. So anything that maps onto Z cannot have property T. So for example, if M is a manifold and the first homology of M with real coefficients is non-zero, then this implies pi1 of M does not have property T. And that says something, turning it around, that's quite striking about manifolds whose fundamental groups have property T, if we can construct any of them, which is the following. Suppose, so let me first note, this is not quite obvious, but it's true, that if G prime is contained in G, and G has T, and this is contained with finite index, then G prime has T. And the proof of that is almost the same as this proof, except now the G is here, and sorry, let me not say it that way. So we have an inclusion of G prime into G. So we need to analyze representations of G prime, and G prime has a supergroup G. Well, there is a way to take any representation of this subgroup and turn it into a representation of G. And we'll talk about that when we get to the proof for certain specific groups. But this is something that is very important, very useful to learn, is extremely general. It's the theory of induced representations. So when you have a subgroup of finite index, every representation of G prime extends to a representation of G into not quite U of H, but into some slightly larger U of H prime. And the analysis of this induced representation can be used to show that G has property T if and only if G prime has property T. Okay, so it's closed under passing to subgroups of finite index or to supergroups of finite index. Those don't change property T. And the reason I bring that up is that if we had a manifold M, if pi1 of M has T, and M tilde is a finite cover of M, then this implies H1 of MR is, and M tilde is still equal to 0. So these groups, if you have a manifold whose fundamental group has property T, not only does its homology vanish, but its homology vanishes on all finite covers. You can never find a cover which has non-trivial H1. And this is very strange compared to what we know about, for example, hyperbolic manifolds or certainly surface groups. They have lots of covers which have non-trivial first homology. And maybe I should add here that, of course, surface groups are not T, again, because of the fact that they admit maps to Z. Okay, so that's like a little panorama of what property T feels like, but now you should be hungry for knowing one example of an infinite group with property T, because I haven't put any down over here. I put down some properties, but no examples. So what we are going to prove is the following theorem. SLNR and SLNZ have property T for n greater than or equal to 3. And in fact, there's a more general theorem due to Kazjan, which I'll just record, that says if G is a semi-simple Lie group with real rank greater than or equal to 2, this implies GS property T. Now, what does the real rank of a Lie group mean? Roughly speaking, it means that you look for the diagonal matrices in G, if it's a matrix group, and you look at what's the dimension of the diagonal subgroup. So, dimension of the diagonal subgroup. That's an abelian group, and it's isomorphic up to finite order to R to the n for some n, and that's called the real rank of the group. So the reason this theorem implies this theorem is that the diagonal of SLNR looks like what? It's A1 up to AN, but then there's the condition that the product of the AI should be equal to 1. So for these groups, the real rank, so like this, is equal to n minus 1. So SL2 does not qualify, but SL3 does. And by the way, this theorem is false for n is equal to 2. Neither SL2Z nor SL2R have property T. Right. So let me just say a word about that before we erase all the non-property T statements. So SL2Z does not have T. And the reason is, one of the many reasons is that inside of SL2Z, we have with finite index this group gamma of 2. That's the group that's generated by 1, 1, 0, 1, and 1, 2, 0, 1, and 1, 0, minus 2, 1. It's essentially the fundamental group of the triply punctured sphere. So this, at least modulo plus or minus the identity, is a free group on G generators. And consequently, SL2Z does not have property T because it has a finite index subgroup that does not have property T. Put differently, there are subgroups of SL2Z that uniformize Riemann surfaces of arbitrarily large genus. These congruent subgroups have that property. Once you have large genus, you have non-trivial homology, so you can't possibly have property T. Okay, so that is our next task, and maybe our final big theorem for this course is that these two groups do indeed have property T. And one thing I like about this theorem is that it brings into play some results that we've already done that by now should be familiar to you, hopefully even almost internalized, like, oh, that feels right, or it's almost obvious. So the proof of this theorem is going to depend on just 3 basic principles. And we're just going to apply those principles, and it's going to come out very easily, surprisingly easily. So this will depend on the following facts. So the first fact is that there is no SL2R invariant measure on the circle. And I think it's remarkable that this deep property about all representations of some fairly complicated group actually hinges on something that's almost intuitively obvious and low dimensional. So we've discussed this many times. I'll come back to it just since we are going to use it. The second thing it's going to depend on is the Mohr Theorem, which says that if if SLNR is ergodic, then it's mixing for n greater than or equal to 2. So this, I hope you remember, is something we proved first in the case of SL2, and then we kind of leveraged it to do it in all cases. But it's like the fact that, once we know that the geodesic flow is ergodic, then we can prove the geodesic flow is mixing and the horizontal flow is mixing on any surface. This was one of our basic bootstrapping operations. When you have a large group acting, ergodicity can be leveraged to get mixing for all the elements of the group. And actually, all we'll need from this is a fairly simple statement, which is that mixing implies every non-compact subgroup is ergodic. In other words, has no invariant vectors. And so here, I should emphasize that by ergodic, I mean for all unitary representations of SL2R. And of course, ergodic means no invariant vectors. So if this has no invariant vectors, then none of its subgroups have invariant vectors. And the final tool we're going to need is what I'll call the spectral theorem, which again is a tool that we've been using since the beginning of the course. We especially did the spectral theory for the case of a single transformation, a single ergodic transformation, where we got a spectral measure of the circle and multiplicity function and so on. We're going to use here the spectral theorem for the group R. But just slightly more general than the spectral theorem for Z. It's like the Fourier transform versus Fourier series. So let me remind you how this works. When we have a locally compacted abelian group, we have its Pontryagin dual, which is the Hom of P into the circle. And in this case, that's just isomorphic to Rn again. And the way it works is if we have an element C in this Rn, and we have an element X here, then we define the character of C evaluated on X to be e to the 2 pi I times the inner product between X and C. So, technically P hat is isomorphic to the dual of P as a vector space. And then the spectral theorem says that when we have a unitary representation of Rn, that it decomposes into a direct integral of representations over P hat, one for each of these characters. So it says that if P maps into the unitary representations of H, then we can write H as the integral over P hat of HC with respect to some spectral measure, d mu of C. And then the action of P on this space is very simple. If you take an element X, it just multiplies an element in this Hilbert space HC by the character chi C applied to X. Okay, so I just want to put those three things on the table and warm them up, keep them in mind, and then next time we'll use them to establish property T. Okay.